same thing, we're going to explore the cosine function. Okay, so let's say we have theta and cosine theta. Again, we're going to take a look at our unit circle once I draw a vertical line here. Okay, so let's say we have our unit circle here, our quadrants. So let's say we start at 0, of course. So our cosine, our x value at the angle of 0 is actually going to be 1 on our unit circle, right? And then let's say we go to pi over 6 for theta. Then our cosine goes to radical 3 over 2. Then we go to pi over 4. Pi over 4 gives us an x value of radical 2 over 2. Pi over 3, or 2 pi over 6, gives us an x value of 1/2. And then pi over 2 gives us 0. Okay, let's do one more, just for the heck of it. We're going to say 2 pi over 3, and that would give us an x value of negative 1/2 now. Okay, so let's just graph these and see where our graph is going. Okay, so here's theta, and here is cosine theta. Again, we'll go from 1 and negative 1 on the y-axis there, or on the cosine theta axis. Now let's do something like this, where this is pi, this is 2 pi over here. Okay, so if we just graph the points that we have 0, 1. So actually we're starting here when our angle is 0, okay? And then we see that as we go along, we kind of, our cosine theta values, or our x values, are dropping, okay? So let's just pick a nice even point. So that would be pi over 2 is equal to 0. Or when you plug in pi over 2, you get 0, right? So we're actually going to see a drop like this, kind of. Okay, that's how it drops. And then at pi, we're actually going to see, okay, so when we're at pi, then our cosine theta is going to be a negative 1. Okay, so we're going to be all the way down here. When we go back to 3 pi over 2, to right here, our cosine value, our x value, is 0 again. Okay, and then when we go back to 2 pi and we return, we're going to go back up to positive 1. Okay, so our cosine graph actually looks something like this. It's kind of like a valley, sort of. Okay, so something like that, and then we'll see, actually, let me extend it out here and let's see some more of this graph. So let's say this is theta, this is our cosine theta. Let's say this is positive 1, here's negative 1. Let's say, okay, so this is pi, 2 pi, 3 pi, and 4 pi. Okay, so here's pi, 2 pi, 3 pi, and 4 pi. And let me go in the other direction too, just for a good measure there. Okay, so that's negative pi. So let me just draw this one cycle that I drew before. Okay, just draw those lines in there. And it looks like a V, but it's actually curvy. So make sure to distinguish that. Okay, so we go up like that. So that's one cycle. Okay, and then it actually just starts over again, because once we're back to 2 pi, that's kind of like starting at 0 again. Our reference angles are going to be the same as we go around the unit circle. So we're actually going to get this repeated pattern, okay, where we start up, go down, and then return back up again. Okay, and the same thing happens on the left side. We just have something like that. Okay, so now we see, if I break this into kind of like frames, sort of, or cycles, here's one. Okay, that's when we run around the unit circle once, and then our next time that this pattern repeats is right next to it, and as is on the left as well. Okay, so again, if we do the same thing here, if we pick a point, let's say pi over 2, 0 for this one, and we pick a point in another frame, so kind of like in this frame here, where our point is exactly at the same point there, or in the same place, then we see that the difference between these two input values, so this one is pi over 2, okay, and this one is 5 pi over 2. So again, we see a difference in those input values of 2 pi. So that's kind of like the horizontal shifting that takes place. We basically just shifted all of the points from frame 1. We shifted them all by 2 pi. We added 2 pi to them, okay, to the input value, and we got the same exact thing. And likewise, we could take everything, all of the points in frame 1 here, or the middle frame. We're going to subtract 2 pi from each of their input values, from each of their thetas, right? And then we get the same thing on the left here, that repeated pattern there, okay? Okay, so let me just recap a little bit. So a period, formally, this is the smallest horizontal shift for a function we could actually say for function values to repeat their pattern. Okay, to repeat their pattern. Okay, if I can spell here, pattern. There we go. This is also the time for one full cycle. One full cycle to occur. Okay, so for that section of the pattern to repeat and repeat and repeat. So for sine and cosine, specifically, as we've seen on the past couple slides, the period, which sometimes is represented by capital T, sometimes it's represented as capital P, either one, they both mean period. For sine and cosine, the period is going to be 2 pi, okay? Also, if we look at it, let's draw our sine and cosine graphs again. So let's say we had something like this for sine, right? And then cosine just started up and went like that. Okay, so this is sine, and this is cosine. Alrighty? And we actually had a maximum value of 1 and -1 for both of these graphs, right? And that's because when we're on the unit circle, we can't have an x or y value greater than 1, right? Because our circle has a radius of 1, so that's impossible for sine or cosine to go beyond 1 or -1, okay? So what we can say about these is that the domain, okay, I'll just write it out. So the domain for both our sine and cosine is -infinity to infinity, because we can basically just plug in any angle we want, right? Because this is the theta axis, so we can plug in anything we want. So we can go all the way to the left, all the way to the right. We can plug in whatever we want. But our range, like I kind of alluded to a couple seconds ago, is we only get output values between -1 and 1, including those values, right? Because we can get -1 and +1, but we can't go beyond those because our unit circle doesn't allow that, okay? So just a quick side note here, the word sinusoidal, which is the title of this concepts video, so sinusoidal graphs basically just refer to sine or cosine. Really, it's just a really fancy name for sine or cosine. You can refer to those both as sinusoidal graphs. Okay, so now let's look at a fun feature of both sine and cosine. So let's do sine first. So let's say we have, so the y values, so here's x and y, right? So let's say this is theta, right? So our sine would be this much, right? So this would be, our y value here would be y is equal to sine theta, okay? Now let's say, what if we were to take the angle negative theta? So that just means the same, you rotate the same amount of degrees, or same amount of radians, but just in the opposite direction, right? Then we would just get the negative of that, right? So this corresponds to this y value, and then this y value would be given by negative sine theta, right? That would just be the negative of it. So that means when you plug in, this means that when we plug in a negative angle of something into our sine graph, we'll simply just get out the negative of whatever we would have plugged in if it were just positive of an angle, okay? So let's say we were to, I don't know, rotate something like this. Let's say we just plug in pi over 6, okay? This is pi over 6, so sine of negative pi over 6 would just be equal to negative of sine pi over 6, okay? So then that would just be an answer of -1/2. Okay, and this relation up here, this one up here that I'm boxing right now, that means this kind of alludes to f, a function where you plug in the negative of something is just equal to negative of the function when you plug in the normal, like the opposite of that, okay? And this characterizes what's called an odd function, okay? Odd function. And odd functions just satisfy this equation here, okay? So basically when you plug in the negative of something, you can pull that negative sign out in front, and that's what you see here. Okay, so now let's look at cosine. Let's see what happens in this case. So let's say we have the same thing going on. We rotate an angle theta this way, and we get a certain x value, a certain cosine. So that would be x is equal to cosine theta, right? And then let's say we rotate negative theta in the other direction. Okay, so then our x value is actually the same, right? X is still equal to cosine of negative theta. All right, so that means that we have something like this. Cosine of negative theta, even if you rotate in the opposite direction, it's still going to be the same x value as if you rotate in the positive direction. So this negative sign can kind of be neglected, right? Well, not neglected. I mean, it's good to acknowledge that it's there, but basically you can just turn it into the positive version. Okay, so this relation, when you can just plug in the negative of something and get out your normal value, this is called an even function. Okay? So cosine is an even function, sine is an odd function. Okay, so now that we've learned about the standard, like sine and cosine graphs, now let's do transformations. Okay, so how do we transform these graphs and what do they look like? So transforming sine and cosine graphs. Okay, or aka sinusoidal graphs. So let's start with the easiest thing, and that would be vertical shifting. Okay, that always seems to be the easiest, right? Because you just add something or subtract something from your function, and then you just add or subtract anything, that same value from your outputs. Okay, so an example of this would be something like f of theta is equal to cosine of theta plus k. Okay, and this plus k is kind of just like something tacked on to the end, and basically that just means you'll have your normal cosine graph, but it'll be moved up by a value of k. Alrighty? Also, we could have something like this, the exact same thing, but for sine instead. So we could have our normal sine graph and just move it up or down by a certain value k. Alrighty? So let's do an example of this. Let's say f of theta is equal to cosine theta. And we'll do, not plus 2, let's do minus 2 instead. Let's do minus 2. Okay, so in this case, we actually have cosine theta plus like a negative 2. Or this is like our k. So k is equal to negative 2. Alright? So actually what our graph is going to look like is the following. So let's say we have, normally, let me just do the parent graph first. So this is our, I'll just make it our y. Okay? So this is f of theta, right? So we have 1, positive 1, here's negative 1, negative 2, negative 3. We're going to need that for later. But let me just do the normal cosine graph for now. Okay, so here's pi, here's 2 pi. So normal cosine starts at 0, 1, goes down to 0, and it goes like this, right? Kind of like a valley. We roll down the hill and then we roll back up. Okay, so that's our normal cosine graph. And now what this is saying is we need to move each of these points down by 2 units. So if we move this one down by 2 units, we get that. If we move this down by 2 units, we get this one right here. If we move that down, we get something at pi negative 3. Move that one down, and we move this one down. So our new graph, our transformed graph, which was vertically shifted down by 2 units, now looks like this. Okay? And so that's basically it. You just move all of your points down by 2. So what we can also see is that, let's compare the original graph with our transformed one. Okay? So our original graph was actually, it looks like this if you extend it out in both directions, right? It'll just keep going and going. And the midline, what's called is the midline. So let me define what a midline is first. Midline is equal to the line, the horizontal line, that is, horizontal line about which, or around which, your function oscillates. Okay, and what does oscillate mean? Oscillates just means goes up and down. Okay, so here it's going up and then it goes down, and then up and then down, and then up and then down, etc., etc., right? So for our original graph, our midline was around the line y is equal to 0. Okay, and then we see for our transformed graph, our midline, if we extend this out in both directions, it would kind of look like that, right? And it oscillates, it goes up and down around this line here, this horizontal line, which is y is equal to negative 2. Okay, which is something interesting because that's what our k value was, right? So this means that for vertical shifting anyways, when you shift something, when you shift a sinusoid, or sine or cosine, when you shift that vertically, your midline shifts as well by that exact amount, okay? So the midline, let me write that on the next slide.